Yes, thank you. Thank you all for joining. So I'm going to show you a application of the QVTo language. It's a language that can be utilized to implement model-to-model transformations, and we apply that to our own developed ESL with MSL and Dezyne. But first, a little bit of context. I work at Philips Online Therapy, and I'll show you a very short fragment of a video. It appears the video doesn't work, so I'll quickly talk you through it. So we develop interventional X-ray systems, such as we see in this picture. And you can imagine that it can move along a railway, and can move like this, can move in all kinds of directions. And it is used for treatment of mainly cardiovascular patients. So we can imagine that the patient is on the table, and we have the X-ray source on the bottom of the arc, and then X-ray detector on the top. And we take images of patients lying on the table. I'm also visible for the people turning around. So, what do we have? We have developed a domain-specific language in the past called the movement specification language, which we use to describe the behavior of our movements. So, longitudinal movements, lateral movements, negative direction, positive direction, you name it. What we have to do, we have to, of course, develop our modeling instance in our own ESL. We have to then, we can then generate C++ code, and that C++ code we, of course, have to test very extensively because we don't have embed in our code. And the maintenance on this code generator is done by ourselves. And the maintenance on the code generator, it's quite a considerable effort, but it consists of approximately 4,000 lines of code. And also testing takes a lot of time, and we would like to shorten the process of testing and maintaining our own code generator. So that is why we wanted to transform our DSL instance of the MSL to Dezyne, which is a toolset that was developed by another company called Wiericx. And it consists of the Dezyne modeling language, model checker, and a C++ code generator. And it contains capabilities to check for deadlocks, line locks, and compliance. I'll zoom into more detail later, but and you can check some custom properties. And the main power of Dezyne is that you have your design model, which can be used to generate a formal model of the design model, and it can be used to generate C++ code. And what Beyond guarantees is that these two models are in behavior equivalent to each other, which I think is a very powerful feature. So what is it that we want actually? Well, as I mentioned on the left here, our current situation, we have our MSL instance that is developed by our developers, which generates C++ code. And another thing a developer needs to do is develop tests for the MSL instance. And this can be quite a time-consuming process. What we actually want is we want to have that the developer still develops the ESL instance of the MSL, and we can generate design models for that. We can use the model check of Dezyne to verify certain properties, and then we generate some C++ code. So that we reduce the amount of testing that we would require, and overall code quality. So that's the idea. So that is what we have used QVTo. So what is it that we actually developed? Well, we have our own MSL, which conforms to ECOR, which is part of the Eclipse development framework. We have created the realm of the MSL ourselves, an instance of course. Then we have a QVTo, which also is developed in the Eclipse modeling framework, and we develop a QVTo instance ourselves. And then we have on the right, we have our design models, which is also developed in the Eclipse modeling framework, which we generate. So the green parts we write ourselves, and the blue parts is what is generated or provided by us. To us, so a small example. In order to prevent some confidentiality issues with my important, I have this small label example instead of the big machine that I showed you earlier. So we have this sort of Mars label. It has bumpers at the bottom. There's an ultrasonic sensor at the top, and it can drive around. And we have Mars on the right. And what the robot will do is it will drive around on Mars. It will go to these colored areas, scan the color, and then provide some data about it. But of course, what we want is we do not want the robot to collide into obstacles, and so it has a distance sensor on the top and bumpers at the bottom, such that it can detect obstacles and stop in time. So what would some typical requirements look like in our own DSL instance? Well, you will see that here at the top, we have now two lines. The first line basically consists of a condition. So while, in this case, the bumpers are active, what do we want to do? Well, in this case, we want to disable the ultrasonic sensor, because we do not want the ultrasonic sensor to trigger all the behaviors while the bumpers are active, because if the bumpers are active, you are already in a collision. And this applies to a specific set of movements, and in this case, this is all movements the robot can do. And the second line basically expresses that by default, we want to have enabled our ultrasonic sensor and our bumpers. That's what the second line expresses. But there is already perhaps a small issue that you can deduct from this, because the second line is not guarded by a condition. We don't know what the value is of the ultrasonic of the bumper sensor, if it is enabled or disabled. Because the bumpers may be active, then the ultrasonic sensor will be disabled, and the ultrasonic sensor will also be enabled by default. So this is quite ambiguous. And we would like to test for these invalid specifications with the design models that we can generate from this. So to show you an example of a result that we get from our QVTo transformation is that we have a design component model here, which basically states the implementation of a part of our software. This is the design modeling language. And the first line you will see here is reflected over here. And this is very similar to what you would see in a modern programming language. So it will first ask the system if the bumpers are active. If the bumpers are active, well, then disable the ultrasonic sensor as mentioned in the first line. And then we go to the default state. And then here's the second part, which true, because, well, it's not covered by a condition, so it is just always true. We enable the ultrasonic sensor, and you will see that these lines over here will say, well, if the state of the sensor is enabled, or if it's not set, then it is most important. If it is not enabled, all is not set, then we are setting a conflicting cyber value, so we mark it as legal. And this is basically to tell the model check that we would like to prevent such as an attack. What were our results for this? Well, we developed a QVTo model-to-model transformation using our QVTo transformation. We could approximately generate 1,200 design models, which sounds like quite a lot. I can imagine. It is because every movement that our system can perform, and every action that our system can perform, so enabling or disabling sensors, setting speeds, gradually stopping, abruptly stopping, a new model is generated because these are all cases where something might go wrong. Using our model-to-model transformation, we were able to detect 17 violations in our serial software, so the machine that we saw at the beginning, concerning the ambiguous sensor status property. And we also found 4 violations concerning the conflicting speeds. So you can also set speed using that language, and we also found violations for that. Unfortunately, we were not able to verify all of our generated models because some of them have a very fast state space for the model checker. So it took too long for the model checker too long, not in an acceptable time period to give us some results. And finally, we could use the generated C++ code in our software and put it on the machine and actually see the generated C++ code writing, which was very nice. So conclusion, by introducing the design toolset in our development chain, we can generate consistent C++ code, we can verify certain properties of our software, which has the advantages of lower maintenance cost from our side because the QVTo transformation contains less lines of code, and we can basically get rid of our C++ code generator that we have. And of course, we have reduced effort in testing our Amazon models. That's all basically it.
Please, questions?
How do you deal with those enormous state spaces like 107?
Yes, that's a very good question indeed. We have explored some approaches for that, but the main issue is that there were some conditions, as I mentioned earlier, that consisted of a lot of variables. So like 21 variables in Boolean, but you can imagine that will go to a very huge size. So we would have to think of ways to maybe reduce the conditions or merge some
reduction techniques.
Yeah, some reduction techniques indeed. Or perhaps we are still looking into that. So more or less no question.
Other questions? Now from me. So as MSL banks with the DSL,
Yes.
can you evaluate it in some way to measure how the users effectively use that language? How it's easier the process of modeling before executing transformations?
Well, I haven't particularly asked myself, but I have the idea that most of the developers like it. I mean, it's a very concise way of specifying our movement behavior. But one complaint that I do here is that it is sometimes quite challenging to debug errors in the sound set. And that's also one of the reasons why I want to move forward to design, because then you can use the toolset to simulate your models. Which makes it more easier to debug.
Yeah, anyway, it's something that can be or should be measured.
Yeah,
In general,
yeah.
to know how you raise the level of efficiency in specifying anything, and also instructions that will be then operationalized by transportations.
Yeah.
Okay, some other questions, please? If not, thank you very much again. Yeah.